Well, I had an idea about mathematics. It's like 3 a.m. But I was thinking about, where does it come from? Yeah, I was thinking about non-local hidden variables and how the idea seems to appear in relativity, where the non-locality of the representation is that you represent the functional relations rather than concrete values which you then compare. So if you think in terms of the functional relations and you construct the functional relations, you can capture the idea of a hidden variable better than otherwise. It just doesn't make any sense if you think of it as a concrete element like a real number. The idea of a hidden variable being a real value is hard to understand, because we think of real values as being constructed elements in some process, like completing a closed field. And if you think of those things as there, the idea of them being non-local is impossible to contemplate. And the idea that I had is incredibly vague because I don't write anything down. I do everything in my head. But the idea is very vaguely, but I'm hoping that the vague description will be more likely to inspire somebody to do something interesting with the idea than if I had written it down in a concrete form full of particular equations, because there are a lot of different ways you can represent these things. But the idea is that a non-local hidden variable can appear as a kind of Galois connection between two different representations from two different points of view, like from two different inertial reference frames. And you have a metric space, and those three metric space are there three? What are they? Metric spaces are to do with basically trying to put a kind of order on elements so that under certain operations of addition, isn't it only addition that you need? You get a kind of consistent point of view from both sides. I once spent a whole weekend at home when I was living in Cambridge thinking about this, and I neglected to explain that I was thinking from the point of view of this idea, which I now call a non-local hidden variable. At the time I didn't even have a name for it. I was thinking in terms of some very abstract idea of two different coordinate systems with no common data. In other words, there's no fixed point mapping one to the other. So there's no reality checkpoint, as it were. And I saw something in those metric space axioms, because a metric space is an undefined object defined axiomatically, that it satisfies certain things like the triangle inequality and like the fact that the distance from a point to itself is always zero. And some minimal axioms, and then whatever you put in there that satisfies those axioms is a metric space, but in itself the metric space is undefined. So it's an abstract set of relations that hold between functions mapping points of some space onto a norm or a distance. And I think that the conundrum with problems of deciding simultaneity and producing objective concrete representations of the Minkowski space goes away if you go to if you start thinking of it in terms of functional relations. It just isn't a problem anymore. Special relativity just seems weird because you try to relate it to the real world where it never actually applies. And the really irritating thing that I found with descriptions of special relativity with things like the twin paradox, where they say, oh, well, if one twin goes on a big long round trip, well, immediately that doesn't apply. Special relativity doesn't apply because a round trip can't be an inertial reference frame. And I'm excluding here some amazing cosmological model where you could have an inertial reference frame that comes back onto itself in a closed universe or something. But anyway, those things just aren't illustrative. Those are awful examples to use. The fact that shit appears in any physics course is a disgrace, because the postulates of special relativity forbid precisely that. You cannot say that special relativity produces the twin paradox. It's bollocks. It would be a much more interesting theory if there were a smooth transition from inertial to inertial to non-inertial reference frames, so that you could actually and this is terribly, but I suspect that what will turn out is that when you go to non-inertial reference frames, those paradoxes disappear. And that's really what physicists are sort of maybe trying to say when they say, oh, well, the twin paradox isn't a real paradox because one of the twins is accelerating and the other isn't. Well, yeah, you've actually got something interesting there, but don't try and say that that's something to do with special relativity. It's not. It's something to do with general relativity. So what this indicates is that in general relativity, there probably is a this stuff isn't a problem, and simultaneity is not a problem anymore. And so you have a much better way of thinking about things like the EPR paradox, or the EPR experiment, or whatever the hell you want to call it. The one involving special relativity and simultaneous spin measurements and things. You have a much better framework on which to tackle problems like that. If you don't start with some complete crap about simultaneity and so the idea is look at non-local hidden variables in terms of Galois connected functional relations between metric spaces, and I think you'll find that you can produce a network like a gauge field with patches, which some people call charts, don't they? Maps, charts, and which combine together into an atlas of the whole space. And I think you'll find that it's okay, and that provided you have more than two charts, you can produce a consistent mapping between any two, and you have the inconsistencies, like in that example that I gave in one of those things I wrote about mapping the names of the days of the week in different languages in different regions on the earth together. You always have a discontinuity, but you can always make sure that the discontinuity is not at the point where you're contemplating, and you look for a picture which is consistent over the whole with all the events that you know in the other frames. And what you'll find is that the places where the inconsistency is are always hopping out of the way. And your aim is to kind of generalize that model in such a way that it can continuously accommodate new patches and new data, new datum with measurements in. New data with measurements in different charts. These charts overlap, and the idea of, it's Lagrange, isn't it? So the idea then is to take these metric spaces, and what you do is you treat the completion of the metric spaces as a process that produces a congruence on both sides of the mappings from one to the other. Excuse me. And I think that would be a much better basis for treating relativity, so that you have one theory that covers both parts. I'm going to stop because I can't speak anymore. Well, that's quite cool. It turns out you can actually pause the thing during the recording. Amazing, because you can't do that with the fucking camera. The software on these phones is absolute fucking bollocks. The stuff that they put on is just next to useless. And then the stuff that Google provides is even, it's fucking awful. I am so sick of crap. It's incredible how bad stuff has got. I don't know why it was like that. Yeah, so gripe. I still can't talk. I haven't got any drink, and they won't give me any money till Tuesday. So good night. Another thing that I forgot to say. This is about. Oh yeah. When you're doing this, from a computational point of view, you'll find that there's an efficient way of computing these metric spaces. If you go and try and look up or figure it out again from scratch, David Wheeler's algorithm for computing binary logarithms, and you get a way to handle irrational coordinate systems from that, I think. So you get I think you get all the algebraic points. Because you've got a whole function space sitting on top of this. Because halving binary numbers is easy. You just shift them one place to the right, and that's taking the square root. If you do that with a logarithm, you're getting the square root of the number. So you can build this up as pairs of functions and their inverses. A log and an exponent function, which will give you operations of square roots and stuff. And you need those to calculate your distances, typically using Pythagoras, So that whole numerical level will be quite easy to incorporate into the model. And the way you should use one of these Cuso and Cuso logical frameworks, Galois connected logical frameworks, to develop this whole theory, so that you can build the computation into the closure process. And you'll find that it's much easier to design a system which only computes the required number of, doesn't compute more precision than necessary. Using fixed, using floating point representation, like single, double, quadruple precision, is just so fucking wasteful. It's stupid that we do that. You need a system that adapts automatically to compute, depending on what context the number is being used in. You want to compute a different accuracy. And then you use this idea of transfer functions to know when to stop. You're looking for an invariance in there. You're looking for congruence up to the transfer function. And ultimately you'll hit something like a display resolution, where computing more bits isn't going to produce any different display, and that's where you stop. So there's a lot of advantages of doing this, and what you've got to start with is Cuso and Cuso's 1970, I think it was 78 or 79, Sigplan or Popple, Sigplan paper on abstract semantics or whatever it is. And you'll have a really nice system to do maths in. And also look at all of Tibby's fucking weird and beautiful maths lectures, Bob Ross style. I still haven't looked up Bob Ross, but she's brilliant. Yeah, okay, I think I won't do any more podcasts tonight. This is fun though. I will do one more. This is about how you go about, you've got two different militaries, Russian and American, and they need to be able to do these, what Winston Churchill called cross bearings, automatically. They need to check each other's cross bearings. So what you do for that is you design a protocol so that they can pass computations to each other to do. And you'll find that there's a famous Galois connection, which is the syntax and semantics Galois connection. So you repeat the process at the kind of communications level, where you have this unity of opposites, so that the computations that the US military send for the Russian military to do, the Russian military are modeling the US military's syntax, and the US military are modeling the Russian military's syntax. And I think the fixed point you want to start with is this unity of opposites. And that will give you the conditions for the congruence that you're trying to produce. So this structure keeps filtering all the way down. All these layers, it works all the way down. So definitely go back and look up that Dijkstra lecture at Newcastle. The one where he ends up saying, and I would like to go on and explain what all this has to do. It's the one where he talks about David Wheeler's logarithm algorithm, binary logarithm algorithm. And he says, I'd like to go on and explain how this, he's all the way through, he's actually talking about fixed points, and he says, I'd like to explain how this connects with, how this involves Galois theory, but I can't. God, that's so depressing. And there's also that Sun Systems lecture, which goes hand in hand with the Newcastle lecture. They complement each other. So you look, I put them both on a blog post on my Logic After Thought blog. So you've got a third party to contain the consistencies, I presume, between the Russians and the Americans. But, you know, the way bloody Theresa May was going on in 2017, well, yeah, maybe she was trying to contain all the inconsistencies and do it in a public way, but I don't think that's the idea. Okay, there's one more. So, what you'll find that Euclid, I wrote a bit about this in Guerrilla Logic. Euclid basically uses the 5 common notions, which are basically a definition of equality. He uses them as logical connectives. And that's the ultimate congruence you're looking for. You want, if you listen to the beginning of Abraham Lincoln's, it's not the beginning, it's somewhere in that movie of Lincoln with Daniel Day-Lewis. Equality is another undefined, is axiomatically defined or undefined thing. So Euclid starts that things each equal to another are equal to each other. Then if equal things are added to equal things, then the wholes are equal. And if equal things are taken away from equal things, then the parts are equal. And if coincident things are equal and the whole is less, the part is less than the whole. That's the fifth, isn't it? You're trying to maintain these conditions. These are the kind of elemental conditions without which reasoning's impossible. So in your public discourse, you're trying to conserve this consistency. So you're looking for a congruence of these 5 common notions. So in your process of building up these triads of Galois connected representations, you're trying to preserve these 5 elements, or 5, you want to make the elements common notions. And if you look at the structure of Euclid Book 5, you see that it's the first 16 propositions are I think they come in 5 groups of 3. They apply to integral numbers, they apply to ratios, and they apply to, I think, numbers potential in square only, commensurable in square only. But there's another way of interpreting them as 5 different sorts of objects under which you can reason. And this process is repeated 3 times. So there are these 2 ways of getting 15, and this proposition 16 is proportionals alternate. And I think that will, in this some kind of sense, capture the essence of the unity of opposites. So if you have your congruence is aiming to preserve in 3 different ways these 5 common notions, the model that Euclid uses is beautiful, and it captures all of that in these 15 propositions. And the 16th is it's something to do with the way the inconsistency moves out of the way whenever you consider these mappings pairwise. Awfully vague, I know, but that's how these things go. So that's enough. I'm talking crap now.